Hi guys, it's me Fazil Najib. So welcome back again after 1 week. Uh, so today we will be discussing about an interesting subject. See, physics is all about discussing interesting things. I know, but the basic issue with learning physics is imagination. You need a lot of visualization and imagination, but people tend to imagine less because imagination itself kind of carries a lot of energy. It consumes a lot of energy, so that's why. And mostly people tend to imagine things which are very easy to imagine, like food, sugar, waterfalls, a place where you want to visit, maybe the moon. But if I ask you to imagine a prism, it might just take around like about a minute to create an image of it. Maybe it's something is going on with your neuropsychology. I do not know. I'm not an expert in that, so I am unable to talk. But still, imagination is a very big deal in physics, as once said by Albert Einstein, that imagination is more important than knowledge, because anyone can acquire knowledge. With ample amount of intelligence, anyone can acquire knowledge, but it is the imagination of that person that takes that person to the next step towards progress, towards making use of the knowledge which is available to create, to understand things about the universe. So anyways guys, let me not just keep blabbering and come into the subject of discussion. So today, in the last class, we had left at our discussions about lenses. So we started discussing about lenses. So what are lenses? I had defined a sentence about what lenses should be. It should be something that distorts. Suppose it should be something, a material. It should be a material. It should be a material, a transparent material, obviously. So the material must be transparent. So a material which is transparent and has some optical density to it. So you can call it, it has some refractive index. It has some refractive index because you know what refractive index is. It's a measure of the optical density. So you have a material which has a certain refractive index. So what happens if light ray goes through this material? Its path should change, or something, a process known as, a phenomenon known as refraction should occur. So the entire subject of discussion is itself about refraction. So basically any material can be a lens which has a refractive index greater than 1. Also the material should be such that it kind of distorts the image of an object over here, which could be seen from here. So this is your beautiful eyes. I have drawn a beautiful eyes. I know that's so talented of me, but still, yeah, thanks for the applause, by the way. There is an object over here. Light rays from it travel across the space, enters the medium, the material, the so-called definitive lens, and then what happens? It comes to the other side, and these rays, A, the ray A and the ray B, are bent or deviated toward, or are deviated towards your eyes. So that's how you see this object over here. These two light rays from either edge of the object should get into your eyes, and this was possible only because this material, this lens was there. But in fact, your brain has this issue of interpreting the object in a different way, because your brain sees, or your eyes receive the lights coming in this manner. So it assumes it's coming from somewhere in this fashion, and obviously this ray also is assumed to come that manner. So the entire object appears to be a huge blob, which means the object's image is not exactly what of the size of the object. Instead, the image has certain size to it, which is kind of like large, as you can see in this, and it might also be distorted, because you might have seen a lot of examples where the image seems to be distorted. The best example would be a raindrop. So a raindrop, as you can see, if you stand somewhere and you look into the raindrop, you might even see the entire background greenery through this water droplet. And even there are cases where images, there are even images taken, I mean, there are professional photographers who take images of these kinds of things. I mean, the images of the background coming through the entire water droplet. So all these materials, here our lens is actually the water droplet, and we have another lens, the camera lens of the camera. So these are examples of lenses in real life. So there are basically two main types of lenses are of varied varieties, but our case study will be dealing with a special category of lens. So you can have a plain lens. What is a plain lens? A plain lens is just a glass slab. It's a plain lens. It has the outer surface or the interface are plain. That's all. So that forms a plain lens. So you might have heard people wearing plain lens, plain glasses. Actually, they are specs. So plain specs. So what do they serve? They serve nothing special. They might just filter light, or protect you from dust, or may have UV filters, and so on. So plain lens do not serve any thing better, because light through plain lens just propagate along straight lines. They do not distort the image. Whatever this object looks like on the other side is what it appears from the opposite side. So it's not a distorting type of lens. So it's just a plain lens. Now what about distortion? How can you distort an image? So I might have talked about this particular sort of surface. Suppose if you had a curved surface. Let me use a different color so that you understand properly. So you had a instead of plain surface, you had just a curved surface. Okay, this is just some sort of interface which looks curved. Okay, now imagine a few light rays in this direction. Okay, so these light rays are parallel to one another. Now these might be coming from one single object which looks like this. Okay, so this was your object. So let me just see this was your object. An object emanated these three parallel rays. Okay, so after being incident on this particular curved surface interface, because here it might be some medium 1, and inside beyond this interface it could be some other medium with a different refractive index. So obviously if the medias have two different refractive index, what happens? The only thing that occurs is refraction. Obviously refraction, light travels but then tends to distort. But now you might want to expect the light ray getting into the medium 2 also to be parallel, but is that true? Is that even true? No, that is not at all true, because according to Snell's law, the angle of incidence and angle of refraction are not directly proportional to each other, but instead are related through trigonometric functions called the sine functions. So what happens, whatever light ray entering such a curved interface, if they are parallel, not parallel, beyond the interface, they won't be parallel again. They won't be parallel again because of this, because of the fact that the normal themselves are not parallel, thus making different of thus these rays making different angle of incidence at different points on the surface. So what happens? So this is not what happens. Instead, these rays tend to distort. See, now you can see the light rays are no more parallel inside the medium because of this fact that this is a curved interface. So what happens? They tend to see, in this case it's coming together, like they are all approaching one another. At some point they might all hit or cross, at least cross each other. So this sort of behavior is called convergence or converging behavior, you could call it, because they all tend towards a common point, or they all tend towards a certain location in space. They're all actually converging. The word converging is what it is referred to here for their behavior. So so you know, now you have learned that curved surfaces do not give a straightforward image. Instead they tend to give a distorted image. Okay, so best examples for curved surfaces are spherical lenses. So the best example anybody could give you are the spherical lenses, which are very simple cases. Okay, they are very simple cases. So we have spherical lenses. So what are spherical lenses? Just as in case of a spherical mirror, you have also spherical lenses. So what are spherical lenses? Imagine like you had a, say, you had a sphere. Obviously you need a sphere. So if you had a sphere over here like this of some radius, let me just mark its radius. I can mark the radius with a black color. Yeah. So there is the center. I'll call the center C. We'll know why in a while. And from the center to the circumference, you have radius R. Okay, you have a radius R. Now imagine that this entire sphere is made of glass, made of glass. Okay, so it's like a marble, but marble is still unclear because it seems to be a bit greenish, has a greenish tint. But instead you can just imagine this this glass sphere to be perfectly crystal clear. So it's very transparent, it's so crystal clear. Okay, now see, imagine if I had a machine, okay, I'm using some, I don't know what, I'm using a machine, and that machine has this ability, like it has the ability to scoop off a section of this material, of this sphere. So how to scoop off? You know how ice cream scoops are taken. They use some a spoon. I think they call that spoon itself a scoop, because that's what it means. Like they have this scissor like thing with them, with which they scoop off a layer of ice cream, and you get, when you if you have a cone ice cream, You scoop off a layer of the ice cream and put it on, and you find it's a semisphere, or a hemisphere of ice cream. So similar to this, we just imagine that we have a machine which could cut out a scoop of this entire sphere. How do you want to scoop off? Suppose you bring that machine over here, and then you slice out a portion of this. Okay, a portion of this. Now how do you want to slice it out? So let me just use the machine. Okay, I'm going to use the machine. So our machine is exactly another sphere, another spherical scoop with similar radius to the previous glass material. Okay, so I'm bringing the scooping machine. What happens, I'm placing it sideways. Then what I'm doing is I'm going to cut out this much portion. How much? Let me just shade it. I can shade it yellow. Okay, so we have this much portion. Okay, we have this much portion. So the remaining, see the scooping, let me remind you one thing, the machine which I used to scoop had also exactly same radius. Okay, so I have scooped off a part of the entire sphere, entire glass sphere, and the part that I have scooped off is marked in yellow, is shaded yellow. So let me just isolate that much part so you understand what I have taken out. So there it is, so we have this, let me just mark the radius, the center of curvature. I'm very sorry, it is it's the center of the sphere from which this was taken. Hola, you have a lens here. What you're seeing here is a lens, in fact, and this lens is called a convex lens. This is a convex lens. Now you might be understanding why I called it convex. You might be getting why I called it convex. I called it convex because see the interface on either sides. See, inside this interface, this yellow region is full of glass, and outside it is air, water, whatever medium there is. Okay, so inside the yellow region, under this, see, let me just show you, let me just highlight and show you. See, this material, this is the interface, these are the interfaces, and what you have inside is glass. You have only glass inside, and so now you can see you have a glass material, and outside can be anything. It can be water, air, vacuum, I don't know, even it can be kerosene, petrol, wherever you want to dip it. Okay, there is no particular speciality for the surrounding medium. So you have glass medium and you have surrounding medium. I don't know whatever it is. Let us just call it vacuum meanwhile, or just let it be anything. Okay, so you can see the interface is now curved. The interface is now curved, and it is also the curvature. The curved interface is actually a section of a sphere. So this is actually a spherical section. So this makes a good example of a spherical lens. So you have a spherical lens here, and the spherical lens of this kind, where the interface is bulged outwards, are called convex lens. So these are convex lens where the interface are bulged outward. See, this material inside is transparent, so light coming from this side should enter this material, travel through the material, and go on to the other side. So we will check off the ray diagrams related to spherical lens, the convex lens, a bit later. Similar to our convex lens, we may also form another form of scoop from the previous case. Suppose again you had a sphere. Let me just draw a sphere. See, this again is a, what is it? It is again a spherical material. Okay, it's again a spherical material, spherical glass material. We have a sphere made up of glass, so it is transparent. Let me write it down here. So it is transparent. Okay, it's transparent and it's made up of say glass. Okay, I've just referred glass because in real life most lenses are made of glasses and fibers. Okay, so basically they are transparent material, any transparent material. You can even make lenses out of liquid, which you will be learning about in your college if you follow a degree in physics. Okay, so this is a glass transparent sphere. Now I don't consider the radius of this. I don't want to consider the radius of this sphere because you will know why. Now let me bring our machine, the scooping machine. Okay, this time the scooping machine should be working a bit differently. So I have a green colored scooping machine. Okay, it's green colored scooping machine. Now what I'm gonna do is I'm gonna remove a certain part from this. Okay, how much part I'm going to remove from this blue sphere? I'm going to remove a section of the blue sphere. Okay, and our lens, our machine had a center. Okay, our machine had a center. I will call it C, and it had a radius, say R. Okay, radius from here. So I'm going to remove this much part. So I'm just going to erase that part. Okay, I'm going to erase. So from the blue sphere I have taken this entire, just let me, one more thing, let me make it a bit more clearer because you won't understand how I did that. Let me shade it, say yellow everywhere, not just here but the entire blue sphere. I'm going to mark with yellow. Okay, I guess you see this color to be yellow because if you are not color blind, people tend to see different colors. I mean color blind people. Okay, so you had this yellow. I mean, I'm just tinted it yellow to make it to differentiate it. Okay, I've used the green cutting sphere, a cutting sphere. Okay, now what I'm going to do, I'm going to remove the section which I have inserted. So I have removed this much section of the glass, of that glass sphere. Okay, I'm not that good at editing and erasing, but still I'm trying my best. Okay, just keep up with me. So I have removed that part, and let me just remind you that let me just mark the point, the center of our machine. So we had the machine and its center was this. Okay, that was our center. Now let me bring that green sphere. Okay, let me bring that green machine onto the opposite side. Okay, I'm bringing it onto the opposite side. Now what I'm going to do is I'm going to remove almost a symmetric part from the other side. So which part I'm going to remove? You know, the part that I'm going to remove using this machine will be this. See, so I've removed that part. Remove that. Let me just erase everything around. So the machine, I have taken it back to my garage, and what I am left over with is this part of our previous sphere. So let me just make it a bit more better by removing this much part, so that I can place them on a flat surface. So you here have is another glass material which was cut off into this shape. So what do we have here? We have, see, there is glass inside everywhere. This yellow shaded region is actually glass. Okay, so outside it might be air, water, kerosene, vacuum, diamond. You might be inside a diamond crystal. It could be ice, anything other than glass. but here it is glass inside this region. Okay, it can be glass, it can be anything. Okay, it can be just any other. It only assumes that these two mediums are different, that's all. So it can be anything, it can be anything, but both should be transparent, that's all, and must have different refractive indexes. So you have is a glass here, glass region inside, and beyond this green boundary you have on the other side is the other material. So where is the interface? The interface between this medium and this medium will be this green curved cutout. Yeah, this is indeed the interface. Over here again we have another interface. So we have two sides with a spherical cutout interface. So this is one interface, this is the other interface, which means light coming from this side can go on, pass on to the other side, and vice versa. So everything is going to happen. So in this case it is contrary to what was in the previous one, because see, the interface now is not bulged outward, but it's instead it's bulged into the material. It's bulged into, it's not bulged outward. Over here also you have into bulging. Okay, a bulging which is into the material. So it's such materials, I mean such cutouts, such lenses whose interfaces are bulged in, or whose interface surfaces are bulged in, are called let me use called the concave. Just as in the case of our concave mirror, this is a concave lens. You can see it's into, so it's like cave. Okay, so caves are always into, say, are something that go into. So you can remember this, the name of this lens, as concave lens, using that particular mnemonic. All right, so we have learned about our two lenses, which was a convex lens which has bulged outwards interface, and a concave lens which has interface bulged in. So these are examples of the spherical lenses. These are the example of spherical lenses. Okay, see here the lens, the convex lens, had a curvature which, see, let me just focus on to the convex lens. See, our convex lens had a curvature which was, I mean, the lens interface was curved towards around this center of curvature, around this point called the center of curvature, which was part of the center of the sphere from, or the part of the center of the cutout sphere. Okay, it is the center from which this material, this lens, was made of. And even in this case there is a center around which the interface tends to curve. So there is this center of curvature. So there is a center of curvature for this case also. So these interfaces, so what are center of curvature? Center of curvatures are points in space around which the interface tend to curve around. Okay, so these are the point in space around which the interface of the lens curves around. Okay, wraps around, curves, wraps around. So these are the few things. So what you want to remember from our discussion is that we have lenses. Basically there are several sorts of lenses, but we are mostly interested in two types of lenses, and they come under a special category, and they are known as the spherical lenses. And we had two types of them, and they were the convex lens. They were convex lens, and we had this concave lens. Okay, concave lens. So let me just draw a small drawing so that you remember. If you want, you can take the screenshot. So lens which is bulged out, the interface whose interface is bulged out, and lens whose spherical interface is bulged in. So these are the examples. For your sake, I have taken pictures from the internet to show you, to showcase how these lenses look in real life. So over here we have the convex lens. We have this convex lens. See, convex lens, this is a picture of a convex lens. You can see a convex lens is actually a transparent material and has spherical interfaces, spherically curved interfaces. So it's bulged outward, it's transparent, light ray passes from one side into the glass material and out to the other side. So this is what a convex lens looks in real life. Let me just focus on to the next image. You can see here is a convex lens. See, this is the convex lens. See, you can see the interfaces are bulged outward. Okay, here is a light source which produces green, red and blue laser lights. Actually this is violet, I guess. These are three parallel rays. Okay, parallel rays are indication of light rays coming from an object which are kept at, yes, you guessed it right, at infinity. So these three rays, when they pass through our lens which was the convex lens, see what happens to the ray? They all converge towards a single point. So parallel rays, after passing through a convex lens, converge at a common point. And you might have studied from your lenses, from the portion of your mirrors, this common point where light rays tend to converge was called the focal point, the focus. In this case we have is a lens, so this is the focus of this lens. This is the focus of this lens. And also you might want to think one more matter. In the case of mirror, when light rays as such as these, when they, instead if you had used a mirror and when they were incident on the mirror, if the light rays would reflect to the same side, but whereas in this case, since this is a transparent material, light ray should pass through. I will be in detail discussing about what is happening here, here and here in a video coming in near future. Let me show you another image over here. See, this is a real-time image. You can see again parallel light rays coming from this side, and they fall onto this convex lens, and these rays, after passing through the lens, all converge at a common point, and this common point is again the focus of the convex lens. See, this is a very neat diagram. This is actually split up. This lens has been split up into several tiny prisms, which I will explain to you why they have done that. But anyways, you have this bunch of parallel rays after passing through the lens tend to focus at a point, tend to converge at a point. Just due to this particular fact, just because they tend to converge the rays, convex lenses are also called converging lenses. Okay, they are also known as converging lenses. So just because they converge parallel rays, they are also referred to as converging lenses. So let me show you concave lenses. So we have here is a concave lens. So let me just show you the picture of a concave lens. How does it behave? See, you have kids sitting in the background. As you can see, the girl wearing the blue short, the kid wearing the blue short is visible in real life over here, but when you look that kid through this lens, she appears to be displaced. See, this is the apparent image, this is the object, which means this lens, and over here you can see this kid wearing a red shirt, red tee, and over here you can see a white t-shirt kid sitting over there. These two kids are actually in fact sitting here, but when you view it from inside this concave lens, you can see them sitting over here. Their images appear here. So object is here, but when you view it through the lens, you can see them sitting over here. So this entire bunch of students are actually sitting from here to here, but when you view it from the lens, they appear to fit inside this material. So this is the view from a concave lens. And why do you view it? To understand it, because of one reason, that concave, let me just tell you in advance, concave lenses form only virtual images, and what you are seeing here is actually virtual image of this entire student group. In real life, a concave lens looks like this. See, you can see this outer circle, and you see here is the bulged inside interface. So the glass lens has a bulged inside thing, and over here also it's inside. So you might have seen people wearing glasses of this kind, because they might have some optical defect, and to correct it, they would be using a concave lens. And there are also people who use convex lens to wear for some of their optical defects. So see, on contrary to the convex lens, I mean opposite to convex lens, as you want to expect, or otherwise this is what should be expected, because the interface in the case of a convex lens was being bulged outwards, but in this case it is bulged inward. See, if it were bulged outward, what happened? The parallel rays tended to converge at a point. Okay, so they, after passing through the convex lens, they converged at a point. But here, exactly opposite to the previous effect, parallel rays after passing through the concave lens do not converge on this side. They do not converge on this side. They instead, passing through the lens, diverge. They all go different points into infinity. Okay, say they tend to move apart. Okay, as they keep on moving from here, the distance between the ray increases, which means they are never going to converge. They are only going to do is they are going to diverge away, move away from one another. But when they move away from one another, which means they do not tend to form a real image, which leads to one particular case where the image formation should occur, or when you view it from the opposite side, you might see they tend to come from a common point. See, actually the rays beyond the mirror are actually parallel to one another, but when you view it from the other side, you can see is that the light ray tend to converge on the other side, and that convergent point might be the image of these rays. Okay, so we will be discussing about this special effects later. You have even a better image. See, actually this is not just a concave lens, but it is a plano concave lens. I will tell you the difference between concave and just a ordinary concave and a plano concave. But anyways, the effects are similar. You have three parallel rays. When they pass through this diverging, see, just because parallel light rays are diverging from after passing through this lens, we also tend to call concave lenses by the name of diverging, that would be better, diverging lenses. So we also called concave lens as diverging lens. So this is the image. Okay, this is the image for their basically this is what real life things look like. Okay, so you had this convex lens, you had this concave lens. Now one more thing. I have to say one more thing, and yeah, this was the slide that I was missing. See, there are actually, if in real life we might have spherical cutouts on both sides, and such lenses are generally called convex lens, but in fact they are convex on both sides, so they are called double convex. And you can even have materials with one side plane and the other side being convex, and such lenses are called plano convex. It's a very easy one. You have another form of lens. This is the most common type of lens used in your eyeglasses. Contact lenses all are actually of this form. They are modified on both sides. See, you can see this one side, and both sides are not they are not perfectly spherical, and they are not perfectly plane. So you have is like a meniscus, a shape of a meniscus. So this lenses are called meniscus lenses. Okay, what is a meniscus? To understand what is a meniscus, you just look into a straw, where you can see the shape of the water inside is actually will be either bulged in or bulged out, and that shape is actually called a meniscus shape. Okay, so these three lenses are converging lenses. These three, a double convex, a plano convex, and a meniscus. These three forms of lenses actually converge light, so they come under the category of converging lenses. These three. Now over here is your standard concave lens, which is concave on both sides. Since it is concave on both sides, we call it double concave. Also, we have this similar situation to our previous case, where one side can be plane and one side be concave, and such lenses are called plano concave. So obvious name. And in the case of this diverging category, we also have this meniscus, diverging meniscus. We call it diverging meniscus. And what is a diverging meniscus? You have concave and concave. Here it is convex and convex. So it is diverging here, and there is, these glasses are actually the most commonly used. See, meniscus are the most commonly used optical defect glasses, as are used as optical defect glasses. So these are the various forms of lenses. See, I have even brought in an image which shows the lenses, the type of lenses used inside a professional camera, inside a DSLR. So see, you can see it makes use of all forms of lenses. It uses convex lens, it uses plano concave, several sorts of plano concave sandwich with convex lenses, and there is this concave diverging meniscus. Here it is a plano concave. This could be a plano, not a plano but a meniscus, diverging meniscus, plano convex. See, now you can distinguish between the various lenses used inside a professional camera. So see, it's not just one particular lens, a particular type of lens, but there are different types of lenses used inside. Over here is the ray diagram, which I will be discussing in detail in the next video. Okay, so thank you guys for listening to this lecture. I will be uploading a new video soon, which you will have to follow to continue learning the mathematical side of this topic about the lenses. So thank you guys once again. If you did not understand anything, if you do not follow my content, please do comment and make sure that you convey your inconvenience, and thank you for watching. We'll see you again in the next video.